Shall we start again? Is it on? I don't think it's on. I think it works. I just changed it.
So that is also.
I think everything is. Okay. So we continue with the plus sense. And now I will actually build on what Michelle told you about the structure of the complexes to tell you a bit more about the function and the diversity. So you will also see a little bit some of the same slides, because actually we borrow them from each other. What Michelle has been showing to you, only the black version of them, but you will see that some of the slides are the same. Okay, so we now focus on the microtubule plus end, and we do this because we think that this is where the destiny of the microtubule is determined. So it's an important place because this plus end, it can grow and shrink, and the complement of molecules which are located here will determine whether it will grow faster or slower, whether it will undergo a catastrophe, or whether it will be rescued, and whether it will attach to something, for example, to the cell cortex, or to the kinetochore of a mitotic chromosome. So this is an important place on the microtubule. And as Michelle just told you, one of the key factors to regulate the attachment of different proteins to the microtubule ends is not the only one. There are other systems which are not dependent on end-binding proteins, but for the proteins that I will be discussing today, the end-binding proteins are the key factor. Michelle discussed with you the structure, so I will not dwell on it anymore. And as Michelle told you, EB proteins autonomously recognize growing microtubule ends, and they recognize both the plus and the minus ends when they grow. And today we will discuss this paper in detail. And this is the movie which Michelle also showed you, which illustrates that EB proteins have a weak affinity for the microtubule lattice, and that they have a high affinity for growing, but not shrinking microtubule ends. And this is also shown in this Scheinman graph, where you draw a line through a growing microtubule, and then take this pixel, this image from every frame, put them under each other. So this is the time axis, this is the distance. Microtubule grows, and there is strong accumulation of the growing tip. And during catastrophe, the EB disappears. And then on the shrinking phase, you don't have this accumulation. Here you have the rescue, and the comet-like labeling of the tip is regained. Okay, so this is how this looks itself, and these are the movies that a lot of you have seen, and some of you have even probably acquired. So this is what you see. And there is one very important misconception from these movies, because when you look at these movies, you see all these guys actually moving to the cell periphery, right? So a lot of them originate here at the centrosome, and then go to the cell periphery. Like you would see also if you would be watching transport, you would see vesicles coming out of the Golgi traveling to the cell periphery. So just by watching this movie, you would think that this is also kind of a transport process, that things get transported from the middle of the cell to the cell periphery. And it's actually an excellent system to transport things. And you will find a lot of papers where people have used this idea actually to explain what they see. And I should emphasize that this idea does not necessarily have to be right. And the way to do this is to understand how it actually works is the following. So here you see such individual code. In our lab, we have a very rapid FRAP system with which we can point the laser beam at the growing microtubule end and photobleach it as it grows. It's a kind of like a shooting game. So you have to be a little bit handy because you have to aim a little bit in front. So it's really like a shooting game. So actually, guys are usually better with it than the girls. So also a guy, a microscopy specialist in my lab at Akhmanova did this experiment. So you photobleach the tip. So this is the kind graph of the growing tip. So you can see that it is a comet, so there is high intensity here and gradually decays in the tail. And it grows. So now, compared to the previous Scheinman graph, I showed you the time axis gets stretched, so it looks more steep. And then here you would bleach it. This is the bleach mark. So you see that the comet became dark, but very rapidly fluorescence is recovered there where it was bleached. So here it was bright, it is dark, and here it's recovered again. And what it is telling you is something very important. Is that these molecules are actually not moving together with the tip. They are exchanging here. So the molecules which were here and which you have bleached, they're not stationary because you get recovery. And you also don't see, it's a little bit hard to see, I will show another experiment when you will see that there is really no movement. But so there is recovery. So these proteins actually are not immobile, because one way of thinking about how this comet is formed would be that they copolymerize these tubulin, right? So that they would come together with the tubulin dimers, immobilize here, and then gradually fall off. For example, because the GTP gets hydrolyzed. But what you learn from this is that the exchange of the molecules at the tip is actually faster than the polymerization of the microtubule. And here is another experiment. It is a single molecule experiment, and this I think answers your question, because I had a question about, okay, these comments, maybe they're just tricky because you can't catch quickly enough the polymerization. So what we did here is grow microtubules in the presence of high concentration of red EB and very low nanomolar concentration of green EB. So that you mark the tip with red EB, you see this comment again. Now we acquire here 30 frames per second, so that's why it's so steep. So actually the Scheinman graph has been stretched even more on the time axis. And we watch individual EB molecules as they land on the microtubule and let go again. And what you see is very short events of EB binding. You see some diffusion, and on the tip we see longer binding events. But you can still see that EB molecules come and go. So it's not that one molecule would bind and translocate with the tip of the comet. They just bind, immobilize, and go away. And you can calculate all kinds of parameters from this. And basically what you learn is that you have more of them here because they bind more frequently and stay longer. And what this tells you is that an EB-bound microtubule tip is actually a kind of a diffusion trap. So you have a sea of EBs floating around the growing microtubule, and some of them will come and transiently immobilize at the tip and get concentrated. And this means that actually binding to the tip slows them down. So a growing tip is by itself not a method for the EBs to get from the centrosome to the cell periphery. Wherever they get by diffusion. And they concentrate on the tip, and that's why you see a comet. Yes? Sorry? It also binds to the microtubule.
No, he's asking whether they work with energy.
Yeah.
What energy? Whether there is, but whether you are hydrolyzing ATP. No, you are not hydrolyzing ATP, and this you can see from this experiment, because here we have EB binding. What we have in this system is tubulin. We have GTP, so in principle, I cannot exclude that EBs somehow affect GTP hydrolysis by tubulin. But EBs don't bind to nucleotide in cells, and you definitely don't need any ATP to have this concentration of the EBs at the tips. You do need growth. And you also get binding of EBs to microtubules when you use a GTP analog which cannot be hydrolyzed. So you don't need hydrolysis to have depuration. So we think that this binding and unbinding is not dependent on energy. So like kinesin would need ATP to work. But also what you see from the single molecule experiment, there is no directionality here. It's just really it's binding and unbinding. Okay, so this is one very important message. So by itself, this tip binding is a kind of a diffusion trap, and it's not a processive transport system. It can be converted to such if you would add a kinesin here. And this is what we'll discuss this afternoon. We will discuss a system from fish bees where one of these proteins which bind to the tip actually first works on microtubules and then can immobilize here. And if you will have a kinesin as a part of the system, then you can create preference for the plus end and not the growing minus end, and you can create also directionality, and then you can also actually transport things. Yes? Yes. That's the idea, yeah. Yeah, so we'll discuss another paper today with beautiful structural evidence suggesting that EBs sense the nucleotide that tubulin has bound. Because there is a certain structural transition in tubulin dependent on whether there's a GDP or GTP or some analog or some other form of nucleotide, and that is what EBs sense, because they bind close to the place on the tubulin where this transition can occur.
This is another question. I thought the idea was that the camp is actually just 1, 2, 3 layers, but the signals in this case is better than that.
Yes, so that's a very good point. So people have been trying to measure the GTP cap for years. And there are two approaches. So one is to somehow grow microtubules and then see how much GTP and GDP is bound. This is very, very difficult. This is incredibly difficult because tubulin is a GTPase, so it hydrolyzes GTP, so you also have tubulin which binds to GTP. So there have been quite a few publications, but it's very, very difficult. And then another approach is also actually what is on the poster here, is you can ask how many GTP tubulin, how long GTP cap has to be to stabilize. And then you can find that it can be 1 or 2 or maybe 4, I think. In your case, it was 4, right? So you would need only a few layers of GTP with tubulin to make the microtubule stable. But how much you need does not tell you how much you have. And if it is true that EB proteins bind to the GTP-bound form of tubulin and recognize the GTP cap, then the appearance of the comet tells you that the cap is long.
This is one more question. That is an alternative to the cap hypothesis, the structural cap. You said that the stabilize the chips by breaking out the plates slightly.
Oh yes,
Is there
we don't know at all. So what is this? I think I tried to emphasize this already, so we don't know at all about the structure. And the reason is, so it's also the whole difficulty here that EBs bind to growing microtubules. So it's very difficult to fix this structure. So actually, because you only have them binding when it grows. But growth is a dynamic and irregular process. So it is, I think, fundamentally impossible to crystallize a growing tip. And so we will see today one example of some kind of approximation of this using an unhydrolyzable GTP analog. But beyond that, it is very difficult to get structural information because all the structural information you can get would be based on electron microscopy in some way. And if all the tips are different, a little bit different, then you cannot average. And if you cannot average, you cannot learn much because the resolution of the current methods is not good enough. So we hope that we will progress with better cryo AM to a level where we would really be able to see individual growing tip and really see each protofilament. I think this is one thing that we would need so to do this, but we're not there. Okay? So that's one important point is that the tips, although they look as if they are going somewhere, they're actually not transporting it. These are not transporting EP. Okay, and then that's the picture also which Michelle has shown you, or a variant of this. The important function of EB is to bring all these proteins to the tip. And what Michelle told you, that they are very different, and that many of them have these SxIP motifs present in them in otherwise completely different structural contexts. So you can have all kinds of different domains. And what Michelle also nicely showed you, that actually you can take a protein that doesn't have such a motif, mutate just 3 or 4 amino acids in a positively charged, unstructured region, and with some luck you will get yourself a cluster. Now you can imagine that this can frequently occur during evolution. And actually we have examples that the protein will be plus tracking in one mammal but not in another one. So just because these motifs can evolve very rapidly. And so this is an overview of some of them. So there is no real structural conservation there, but you have these basic features. And one thing I wanted to mention, because Michelle didn't mention it, but which I also find important, is that a very short sequence of 12 amino acids is enough to target something to the plus cells, like shown in this movie here. But actually it works better in a dimeric context, and this is shown here. So here we take a little bit longer sequence, and this is a monomer, and this is a parallel dimer, because what Michelle showed you is that the structure is actually a dimeric structure, because EB is dimeric. And actually this works much better if you have either a parallel or a tandem dimer. So very often these sequences, they are either found in dimeric proteins or they work in pairs. So this is another important point. And then coming back to the question that somebody who was sitting here asked, and this is how many proteins that we would have SxIP motifs. Because with Cabra it's clear, Cabra is a protein, is a domain of 100 amino acids. You've sequenced the genome, you found them all. But what about the SxIPs? So we took a dual approach. So we looked at the sequences, but we already immediately realized, and you all realize, that 4 amino acids, even if you have some constraints for the surrounding sequence, will yield hundreds of proteins. So another thing that we did, and that's what works very well with the EBs, is a pull down. So because this interaction is pretty flexible, it easily forms in solution. And because it's like that, you can just make yourself some GST-EB fusions, which are very easy to purify from bacteria, and just throw in almost any extract and pull them out. And that's what we did. So for bioinformatics, we looked at a bigger range of proteins, and what we have selected is a sequence of 9 amino acids. So the core is this SxIP. And what we noticed is that around this core 4 amino acids, there should be no negatively charged amino acids, and there should be at least 1 positively charged amino acid. And we did this in collaboration with Toby Gibson. And we also looked at the way to rank the sequences, because you can then create a kind of consensus, and then you get a lot of hits, you get thousands of hits. So we also introduced the condition that the sequence has to be unfolded. So it shouldn't be inside a domain which is predicted to have a folded structure. And we also only chose those that are reasonably conserved, because so we thought that if we are looking at proteins where class and tracking is functionally important, because conservation always gives you a good feel of that. And so we got about 800 proteins, and we ranked them because Michelle, in collaboration with another group, has mutated actually in one of the peptides. In this one, they mutated every amino acid and looked at the effect that would have on the affinity to the EBs. And we use this information then to compare it to the naturally occurring sequences and predict which one will have higher affinity or lower affinity. So it gives you a ranking. So we ranked these 800 proteins. And then we also did like about 10 mass spec experiments where we looked at which proteins bind to EBs. And what you find there is, of course, some of the proteins that we know bind to EBs, but you also bring everything in that binds to those proteins. Yeah? So you get a lot of, you get like thousands of proteins. And what we then did, we also ranked them just based on their mascot score, which is basically the number of peptides you find for each hit, normalized it a bit. And so we set out the findings from the bioinformatics search, which we call SxIP score, just based on the sequence, and this mass spec score, which is based on how frequently we find them and how high is the hit that we find. You cannot read the names here, so if you are really interested, so it's all published in Carbohydrates here, so you can have a look. It has a very large table as a supplement, so you can check whether your favorite protein is there. Both the bioinformatics and the mass spec scores are all there. So what I want to show you is that so we colorized some of the proteins red, which means that we knew that they are plus and tracking proteins. And you can see that the ones that are actually very high, both assays, they come up. So for example, yeah, so these are the class. So APC, for example, adenomatous polyposis coli, which was the first class discovered to bind to EBs. Actually, EBs were discovered because they bind to APC. Interestingly, end binding protein, you would think that it's end binding because it binds to microtubule ends, but actually it was called end binding because it binds to the C terminus to the end of APC. That's why they call it AB. But the name stayed, and now everybody forgot where it comes from. And some of the other famous, so one might have two, the one from which the structure comes that Michelle has shown is also here. So these are some of the red ones. So the clips, by the way, so they come very abundantly in the mass specs, but they don't have a good SxIP, so that's why they will be here on the x-axis. And then we selected about 30 proteins that were somehow shifted here, and also some that were just high in the SxIP score that we thought interesting. And we fused them to GFP. And from those 30, which we thought were kind of promising, 20 were plus and tracking. So we already had about 20, and we added 20 more. So we have now about 40 proteins that can at least track microtubule ends when fused to GFP. For some of them, we know for sure that they also do it endogenously. And for some of them, we still have to find out. But what it tells you that actually the proteome at the tip is pretty rich. And that by using this trick, you can also apply it, so people are now using this in yeast and in other systems, in flies. You can actually find what is in your proteome that you are interested in that could be binding to the microtubule end. So it is a good trick which is working. And I call it a zoo at the tip because we really find a lot of different proteins. So it's a real zoo. And I would like to give you some examples. So this example is actually inspired also by a question that somebody asked. So,
That's a great job.
okay, thank you guys, and now all going.
Even faster.
You can watch the movie and
Only in India.
think we're kind of okay, right? You can hear me? Okay. So just to give you some examples of things that you have found. So actually we did not discover that this protein binds to EB. It was published before, but we found that it is a plasmid tracking protein. And the interesting property of this particular protein, it's called DDA3, is it has two SxIP sites, is that it decorates not only growing ends, but also shrinking ends. And that's probably because it pretty well decorates the lattice and collects from the lattice when the microtubule is depolymerizing. So here you see a very pretty depolymerizing minus end, and you see that you get the cone. And this is another example with the same protein where EB is in red, so you can see that some are localizing this DDA green, and you also see that there are some shrinking plus ends like one shown here, which have DDA3 but don't have EB. And I think this answers the question: is do some plasmid tracking proteins persist when you go to the polymerization? Yes, this can happen. We have just one good other example when this happens. And this is probably due to the fact that these proteins also have microtubule affinities, we just discussed before the break, so that they also bind to the microtubule lattice and actually do it so well that they persist in binding to the lattice while microtubule shrinks. By the way, this persistence of binding to microtubule lattice is also probably the principle how kinetochores hold on to a depolymerizing microtubule when it shrinks. So, yes, so some plasmid tracking proteins can label depolymerizing. So that is one thing. And this is another thing I wanted to discuss a little bit, and this is actually inspired by Sandhya's question, is, so do microtubules touch the plasma membrane? So as Sandhya pointed out to me during the break, is that one way of thinking of cell architecture is that you have microtubules, and then you have actin cortex, and then you will have the plasma membrane. So we found one protein which has a membrane binding protein. It's a peripheral membrane binding protein. It belongs to this family of Wilms tumor gene on the X chromosome. There are 3 of these genes. This particular one was called FAM123A or AMER2. So they all have this membrane binding domain, and this particular homologue has 2 SxIP sites. And this is a really interesting protein because it's really on the membrane. Because this is in the here in green. And in red we have EBs here. And I hope you can see here that some tips are red, and some tips are more green and orange. And you can clearly see that some of them are really red, so they don't have any of these green protein at all, and some are pretty well colocalizing, and that most of them are actually the cell periphery. And so what we think this protein is telling us that you can't actually detect contacts between the plasma membrane and the growing microtubule tips, because this protein is restricted in its diffusion to the plasma membrane, and only when the tips would be touching the membrane, and this often occurs at the cell periphery, you would see these comets forming. Because then EB would come into contact with the plasma membrane, and there it will collect the protein from the plasma membrane to the tip, and that's how you will get this label. And one experiment that I didn't put here because you really have to look at it very carefully. It's in the paper. The movies are not extremely good, but one thing that we did is depolymerize actin, and what we saw is that we actually get much more of these tips labeled with this membrane binding protein. What it tells you is that you can have some contacts between growing microtubules and the plasma membrane, but when you don't have actin, or if you have less polymeric actin, you have more of these contacts. So which says that actin probably can form an obstacle for microtubule interaction with the plasma membrane, but that some interactions could also occur even when actin cortex is intact, at least in these cells. Yes?
Is the membrane binding that you have that in there as non-canonical?
What?
Motifs, but it's not.
It is a positively charged lipid binding. Yeah, but it's pretty strong lipid binding, so you don't see much of the cytosolic pool of this protein, and actually the fact that you don't see any of it on some of the tips already tells you that. So it's really restricted, because the contrast here is very, very strong. So it really tells you that it's restricted in the membrane. And another important thing that I should emphasize that again here, if you would photo bleach the green, so what you would see that the green protein first has to repopulate this area, and then you will see comets coming up again. So you would not, if you would photo bleach here, you would not see green comets entering into a dark region. What you would always see first that that particular part of the cell has to accumulate diffusible pool, and then you will start to see the comets. Which tells you again that this is a concentration thing, that you really is a kind of a diffusion trap, and it's not a transport process here. So then to the question that also has been raised, but just to make this very clear, so these comets in mammalian cells can go up to 2 micrometers in length. That's what we can easily measure. Okay, they decay, but if you just count how many tubulins you have on such a length, you end up with about 3,000. And of course, not every site will be populated. You have some decay, and probably the end is also not very regular. But this tells you that on a 13 protofilament microtubule, you would have at least hundreds of binding sites for these proteins. So there is some space for the zoo. And as I told you already, so what you can see from the recent mass spec papers that EBs are very abundant. They maybe are like micromolar in cells, and typically most of the SxIPs would be 1000 or even lower concentration than the EBs. So some of them are abundant, but most of them would have lower concentration. And so in this way, there will be some competition, but you can still fit a lot of different. Okay, then another question, so this is all inspired by some of the questions I always get to when I give this talk. So are all the microtubule growing ends the same? And so I already showed you actually that it's not the case because some of them touch the plasma membrane and then they will have a different composition. That's another pretty example, which actually Michelle and I like a lot. So it's a molecule called strong interaction molecule, or SPIN1. It has been the molecule of the year in 2006. It's a very interesting ER protein. It has a transmembrane ER transmembrane domain. It's sticking in the ER. This part sits in the lumen and senses calcium. And when calcium stores are depleted, this protein aggregates in the ER. The ER would touch the plasma membrane and open channels in the plasma membrane to let calcium in. This process is called store-operated calcium entry. It's very important, for example, for signaling in immune cells, but also in certain neurons that can also play a role. So it is a part of a very important calcium signaling machinery. And we were very surprised when we found that it's actually one of the most abundant hits in some of our EV pull downs. And that's because it has a single SxIP site, which is here at the very C terminus, which is sticking out into the cytosol. And when we made some movies, so the SPIN1 is in green, here's a little bit overexpressed, so it makes these aggregates. But if you just focus here, so it labels the whole ER network. So you see the ER network, and the EB is here in red, so you can see it binds because it also goes with its aggregates again. But I would like you to focus on this part where you see dynamic behavior of the microtubules. And you can see a little bit the same thing as what's happening at the plasma membrane. You see red tips and you see orange tips. So when a microtubule grows and it touches the ER, you get accumulation of SPIN1, and what you can also see is the pulling out of a small membrane tubule. The membrane tubule can release and snap back, and the tip will continue growing and will have no SPIN1 until it touches another ER. And here is another example. Here. So, and that, what it tells you actually that the growing tip is also kind of a sensor of what is around it. And since it is a diffusion trap, it will actually, everything is like a very sticky person walking through a crowded environment. So everything which is around it will stick on it and it will change its appearance. So this is, and that's why different microtubule tips can be different, just because they go through a different patch in the cell. Yes?
So, is it endogenous thing also look like
yeah, so there are no antibodies, although there are like about 10 still papers per month. I haven't yet encountered an antibody that was good enough to have a very good labeling of this, but is it functionally important? So This is another pretty example of a growing microtubule pulling out an ER tube. Now, this process has been known for a long time. Actually, Claire Waterman-Storer has described it already in the 90s, just by observing ER dynamics. And what she has shown that ER tubules can be protruding in two ways. Either a motor pulls it along pre-existing microtubules, or a growing microtubule will pull together with an ER tubule, just as this movie shows. And this process she called the tip attachment complex, because it attaches to the tip. So the ER tubule attaches to the growing microtubule tip, mediated ER protrusion. And what we have shown in this paper, which is pretty old now, is that if you deplete STIM1, or if you deplete EB1, you don't see these events. So we think that this process is important for part of the remodeling of the ER. The problem of investigating its functional importance is that we actually don't know how many of these protrusions you need, and you have this motor-based process. So actually kinesin and dynein can also pull ER tubules by working on microtubules. And they basically completely take over if you knock down this system. So you still have ER network. Yes?
Then I go by the CP9 hypothesis. I was wondering if you can bend the ER so much, could it not even carry just vesicles just by pushing it? Has anybody looked into that?
Yeah, so indeed, when you have, so I was telling you that individually these are not transported, but here you have an active transport process, which also tells you that when you have this very crowded thing, so as an emerging behavior of multiple molecules working together, you can push things. So you could also, in principle, indeed push something like a vesicle, and that's something that we would like to reconstitute in vitro, so I'm still looking for a person who would be interested.
I don't see why not.
Yeah, no, you're completely right. So the biophysics of this still could be researched much better.
What's vesicle transport is kind of stop and go in cells. So could this be one reason, because these microtubules go through the membrane, and then into the membrane kind of get stuck for a while, and then
definitely, yeah. So the one, anyway, crowding can definitely be one. But you can see, so I think what this movie shows very nicely how heterogeneous the whole thing is. Because here, what I like about this movie, that it really visualizes how microtubules, because when you just make this two-dimensional movie, you don't know if they really touch the ER or not. But here, because you concentrate the protein, you really know that they touch each other. So there is a physical contact. So then you see actually how heterogeneous is the environment through which the growing tip goes, and how much so it really encounters stuff, deals with it somehow, and keeps growing, or maybe not. So to just finish this part, so we don't know if this is important. The reason why we're not researching it is because there are like 20 very good labs working on store-operated calcium entry, and we already had trouble enough publishing this, so they almost crucify you when you want to go further with this. So I'm still looking for a good collaborator on store-operated calcium entry to see whether this process is important for some features of the, because one way of thinking about it is that you have to concentrate STIM1 to open those calcium channels. And microtubules grow to the cell periphery, so it would be a very nice way to make a concentrated STIM1, bring ER tubule there, and then have some kind of nice regulation of these cortical residue calcium channels in certain conditions, depending on microtubule dynamics. So there could be systems where that could be researched, but we haven't done this. Okay, so this is one thing that +TIPS can do, push ER tubules. But the other very important function is, as Michelle already told you, microtubule dynamics regulation. And what I would like to do is build a little bit on what Michelle told you about the structure to tell you a little bit more about the function. So Michelle already mentioned these protein SLAINs. They came out of this screen I showed you, and they actually look incredibly uninteresting. So they're called SLAINs. There are two of them, SLAIN1 and SLAIN2 in mammalian cells. They have a short coiled and for the rest they are all unstructured regions. There is no homology whatsoever to anything serious, and there are quite a few sequences which look like SxIP motifs. There are a couple of good ones and a couple of divergent ones. They're called SLAINs because here on the C terms there is a sequence which reads SLAIN, and it's not conserved in SLAIN2. The name was coined by these guys, and so now they just like the name. Although I would probably choose a name that would somehow reflect both proteins and not just one of them. Anyway, so a student in my lab, Babette van der Vaart, although the protein looked so uninteresting, somehow felt passionate about it and decided to investigate its function. And so, as Michelle told you, together with Michelle's group, she showed that there is a very interesting tyrosine here, which actually binds, helps to bind it to CLIP-170. She showed that these motifs are important for EB binding as a plasma tracking protein, and she also showed that it interacts with another plasma tracking protein called CLASP, which I have been working on for many years, and I will not have a chance to talk to you about it today. So it interacts with quite a few plasma tracking proteins, but we still didn't know what it does. And then she did a mass spec analysis, so she just pulled down SLAIN2 and looked what binds. And the most abundant, almost equimolar partner that she found was this protein I already mentioned to you today, ch-TOG, or XMAP215 enzymes. So this microtubule polymerase, which accelerates microtubule growth in vitro. And then we thought, yeah, it's really nice, because, and these are the mapping of the domains. I will not show you the biochemical evidence, but she has done it in a really nice way. So here are the SxIP motifs, which bind to EB and bring it to the tip. And this N-terminal part binds to the C-terminus of this microtubule polymerase ch-TOG. And then we looked what happens in cells. So normally, ch-TOG can be found on the tips, although it depends a little bit on the cell type. It can form comet-like accumulations and co-localize with EBs. And when we knocked down SLAIN2, we saw two things. That is that the comets somehow became different, they were less slow, and we could find hardly any co-localization with ch-TOG. I'm not saying that it's not there, because protein is pretty diffuse anyway, but at least the accumulation at the end was definitely strongly reduced. So we thought that, okay, SLAIN binds to the ch-TOG and helps to bring it to the growing microtubule. So what would the function be? So this is a movie of plus enzyme control HIRA cell. So you see these comments, you have already seen 20 times today. And this is what happens when we knock down SLAIN2. So we still see EBs, but they now become more or less dot-like. And if you count endogenous comets in cells, their number is reduced. And these comets are kind of flickering, they appear and disappear. It's a little bit difficult to see from this movie. So, but it's easier to see from a kymograph. So this is a control situation where microtubules grow pretty processively. Sometimes they stop and then undergo a small catastrophe, but mostly you see pretty processive growth. And interestingly, when we knock down SLAIN2 or ch-TOG, we saw almost the same phenotype. And this phenotype has also been seen by other laboratories. Is that microtubules still grow, but the comets get shorter, and so the overall growth becomes slower. So it slows down. You see that here the slopes are pretty horizontal, and here they become steeper. So which in this presentation, the microtubules grow in this way. So this is the distance, this is the time. Oh, yeah, it's shown here. So it means that this slow, the growth is slower. But actually, when you look very carefully at growth episodes, you see very short bursts of growth. And then microtubule will kind of stop and maybe undergo a very small catastrophe, and then we'll have another burst of growth. So growth gets much less processive. So we cannot dissect it further than this. We cannot say whether it's really very short growth burst and you really have the polymerization events or you just lose EBs. We also did the same imaging with microtubules, just as tubular, and we see the same thing. But it's difficult because here you come to the limit of the optical microscopy. So basically the changes in the length of the microtubule become so small that you go below the resolution limit of optical microscopy. Yes? Something?
If you said the very tiny drop that you see,
yeah.
does that mean the GTP cap also shrinks?
If you think that, because this is a dual argument, right? So if you think that EBs really show you the GTP cap, then yes. Can these two things be dissociated somehow, that you can also have short GTP caps but long comets? Or I don't know, because we don't have any other measurement for it, right? So we say that we think that EBs report on the GTP cap, and then yes, that's the answer. But if they don't, or if the relationship is not one-to-one, then maybe not.
Have you looked at this, Steve?
We have measured the length of the comet. It's definitely short. You can see it very clearly from the movie. I haven't included the plot, but it becomes like twice as short. But again, you come to the resolution limit of optical microscopy because it's like 1 micrometer, they get to half micrometer, but the limit is 200-300 nanometers. Yeah, so I cannot say if it is 100 nanometers or if it's half a micrometer. That's where the resolution of my experiment stops. And since it's a very dynamic process, because you only see these comets when microtubules grow, you cannot apply the super resolution techniques because they are all very slow and have you need either very intense light and they're all slow, so it doesn't help us. Yes?
There's likely to have elements inside the microtubule which are not like which are deepest right away from each other, which are not like that.
So the remnants. So the point with the remnants, so I showed you the paper about the remnants because it's an important paper, it's cited a lot. So one thing we never see with EBs is any trace over the binding to any spots on the microtubules. Never, and nobody has ever seen that. And this actually contradicts the GTP remnant theory very strongly because if EBs see the GTP conformation of tubulin, then I would say there are no GTP remnants, and then what that antibody sees is something different. Whatever that may be, and whether that stimulates rescues, it's not, at least it's definitely not the same thing as EB. So they see different things, no doubt about it.
I mean, you are telling that these high resolution techniques, they cannot see it. So if you want to make it visible to those techniques, if in case of unfold, you will do some of the microtubule and SRNA in these SLAIN cells, and if you compare, can that become the relevant and you will get some more information because you are reducing the speed of the microtubules.
Yeah, so it's interesting, actually it's a very good point. So this type of growth, we also see when we, for example, add low levels of a vinca alkaloids or colchicine. So we actually get a pretty similar phenomenon. So we also get slower growth, shorter comets, and also this kind of flickering behavior. So this a little bit of this stop and go. So the problem again is that it's a dynamic process. It still remains dynamic. So I think that the super resolution methods will get there, that we will be able, because they are getting better and better and better. So we will get there. The whole methodology emerged about 5 years ago, so it's evolving very, very rapidly. The cameras get better, the fluorophores get better, so we will get there. But we are, at the moment, we are not there yet to be able to use optical microscopy to zoom in on what is happening here. Not now. Okay, so you have all these mini catastrophes. And then another thing that we did is analyze microtubule growth processivity. So microtubules grow out from the centrosome in this cell type, Chinese hamster ovary cell. And normally in this cell type, I emphasize on this cell type, they would grow all the way to the plasma membrane. And so most of the tracks of EBs, or if you follow with microtubules, you will have the same, like 80% of the tracks will be longer than half of the cell radius. And if we knock down SLAIN or ch-TOG, then the tracks get, so you have also reduction of nucleation, and then the tracks get really short. So you also, in addition to those mini catastrophes, you also have macro catastrophes. So microtubules really stop growing as such. So we don't know yet whether ch-TOG is really important for acceleration of individual growth events. Maybe we don't deplete enough, but at least the processivity of growth is strongly affected, and SLAIN is needed for this because we think it helps to concentrate ch-TOG at the microtubule end. And so this very uninteresting looking protein actually acts as a kind of glue to bring all these proteins together at the microtubule tip, including this very important protein.
Obvious question, but there is no change in the amount of tubule in these cells.
We haven't measured very carefully, but it doesn't look like that. And actually, the bursts of polymerization, if you look at those individual bursts, they have more or less the same speed. And if you would have a strong change in tubular concentration, the first thing that will change is the overall polymerization rate, because it's exquisitely sensitive to that. We had on one condition with another protein where we could see that. Yes? Maybe you first?
Have you looked at the SLAIN and how you shrinking microtubules?
Yeah, so there are some reports that TOG can also bind to shrinking microtubules, but this is a bit controversial because TOG is actually very difficult to visualize in live cells. There is one close paper where recently appeared where they looked at it in more detail. On stable microtubules, you don't see.
My question is that if you are doing a microtubule associated protein and you are doing and binding proteins, if you will deplete both of those proteins, in which case you will find more effect on the microtubule dynamics.
If you deplete EBs or these?
I mean, it's a general, but I am generally microtubule associated protein, and we are doing and binding protein, and we are depleting both this protein and this protein. Comparatively, this should give more effect on the microtubule dynamics.
So that's a bit tricky because also depends on the level of your depletion and on the system.
Same depletion, we will somehow optimize what's the level of that thing and how much we should deplete.
Yeah, so this is a difficult thing to address because they're all, so I don't have a good answer. So it's now 1 o'clock, so we have two choices. I have still one small story to tell, but I'm also quite willing to stop now and go to lunch. It's up to you guys what you prefer to do. What?
We should get the same.
Yeah, I will try to wrap it up in 10 minutes because Michelle actually already.
Maybe go through 10, 20 minutes into the lunch.
Yeah, so okay, if you are willing to sacrifice 10 minutes from your lunch, that's okay. Okay, so the point is that actually that has been raised here. So, okay, so I showed you that SLAIN has a very strong effect on microtubule growth processivity because normally microtubules have this long outgrowth episode. You deplete SLAIN or ch-TOG, you have very short growth episodes from the centrosome in CHO cells. But then, as I told you, so EBs are so important, right? So that EBs should have the same phenotype. And the frustrating thing is that they are somewhere in between. So they do affect microtubule growth processivity. Microtubule outgrowth from the centrosome will be shorter. You will have more catastrophe, but it's not as dramatic as here. One reason why it's not such a dramatic phenotype would be because we don't deplete everything. There are 3 EB proteins, and we have never managed to deplete them completely. We have tried really hard. And the point is that EBs are 1 micromolar in cells, or maybe hundreds of nanomolar, and in vitro we know that adding 10 nanomolar EB is enough to see everything. So maybe if you have like just a few % of the total pool, they already rescue them. So that's something to keep in mind. So that could be one explanation. But there is another explanation, and that is that there are many different EB binding proteins, and they could have different effects on microtubule dynamics. And then I'll focus on MCAK because that's also what Michelle has described to you. So that's why I can go very quickly. So it is a microtubule depolymerase. It doesn't work on microtubules. It has a kinase motor domain in the middle, and it has 1 SxIP+. And what we did is reconstitute MCAK in vitro on dynamic microtubules. So what you see here is an in vitro assay where we added green MCAK and red EB. And what you can see is that MCAK is +end tracking on growing microtubule ends in vitro. Michelle already showed you that this happens in cells. And what you can also, I hope, see, if you remember the previous chymograph I showed you just for EB alone, you had these really long episodes of growth like this one, and now you have a lot of catastrophe. But what is also important that if we wouldn't add EB in this assay, just 6 nanomolar MCAK, you would not have any growth at all. MCAK would block all growth whatsoever. You will just, it will actually, you will have these seeds because this is the seed. It will just eat up the seeds, and this will be the end of your assay. And if you don't run through the microscope quick enough, you will not even find any seeds when you are there. So this is telling you 2 important things. That EB, on the one hand, it somehow prevents MCAK from completely blocking outgrowth, so microtubules can still outgrow although MCAK is there. And then it concentrates MCAK on the growing ends, although it's a depolymerase. And you get high catastrophe. So we tried to use this information that we got from the structural study that Michelle has performed to learn more about the system. and specifically to ask the question which was open at the time in the field. Okay, concentrating MCAK on the growing tip. Does it promote catastrophe or does it inhibit catastrophe? Because you could see it in two ways. EB is just inhibiting the MCAK pool here, or EB really brings more MCAK here and you will have more catastrophe. So one way of doing it stems from the structure. So as Michelle told you, there is this tail of EB and it structures when SxIP peptide binds, so you get this cavity, and this tail is part of this cavity. But this tail, actually you can amputate it here. You don't need it for EB proteins to exist and to bind to the growing ends. It's just there to bind partners. And if you remove this tail, so basically this ear-like protrusion here, you will have only half of the binding site. So the affinity will be very strongly reduced, but you will still have a plus and track EB. And this is shown here, so this is EB1 and EB3, which lack the tail, so they don't bind MCAK. And if you look at the movie or at the chymo, you can see that MCAK is still on the lattice, but it no longer concentrates at the growing tip when EB misses the tail. And this will work actually for every SxIP protein. So this, you can use it as a control. So if you put in this delta tail, it should bind to your SxIP partners, and it shouldn't bring them to the tip. So if you have a microtubule binding protein and you want to know if the mode of interaction, your hypothesis is that it binds to this SxIP mode, you can just take a tailless version and then the binding should go. And this tells you that this is the same mode as Michelle described, which is useful because sometimes you also have other types of mutations. What is important is that if you now compare the reconstitution of MCAK with EB, which has the tail, so you have these really short episodes and MCAK is at the tip. And if you take tailless EB, so the one without the tail, you can now add much more MCAK, like here it's 4 times more, and you will still have longer growth episodes, which tells you, although MCAK is still here on the lattice, so because it's not concentrating at the tip, you have fewer catastrophes, so it's less potent in inducing catastrophes. But okay, here we have disabled this whole SxIP system. It is useful for this experiment, but it's of course much more useful just to mutate MCAK so that you could do it yourself, so that you don't disable the whole system, you just prevent one protein from binding to the tip. And as Michelle told you, this is easy to do. You just mutate this site, for example, the isoleucine and proline, you mutate them to asparagens. And this is a nice mutation because you don't change the charge so much, you also will not change so much the folding of the whole peptide. So it's really a kind of a minor modification. You lose the binding to EB, and you lose the plasma tracking, as Michelle told you. And what is nice that if you do the same mutant in vitro, again, it will not plasma track, and it will not be able to induce catastrophe as efficiently as what you have the wild-type protein. And so the question is, can we also recapitulate it in cells? And this is one thing I really like to emphasize, because people like to do experiments in vitro, or they like to do experiments in cells. But actually, it's very important to do both, because you can get away with something that you see in vitro, or you just interpret things based on what you see in cells, and it's actually nice when you can compare the two things. So that's exactly the reason why we chose MCAK, because MCAK is a wonderful molecule. If you overexpress it in cells, it will just eat up all your microtubules. As simple as that. So this is an untransfected cell, you see the polymers, and this is a transfected cell, no microtubules at all, or hydrogen. And so the question you can ask them is, okay, so if you have a certain concentration of MCAK, which you can measure based on GFP concentration, and if it can bind to EB or not, whether it will be a better depolymerase in cells or a less good depolymerase in cells. Okay, so we can all now wonder a little bit what is the answer, but the answer actually is that if MCAK has this IPNN mutation, when it cannot bind to EBs, it is less efficient in depolymerizing microtubules. So at the same concentration of MCAK in the cell, you will have no microtubules with the wild-type protein, but you will still have quite a few microtubules when this mutation is there. which tells you that EB, by bringing MCAK to the tip of the microtubule, also makes it a more efficient depolymerize. So it concentrates the MCAK at the tip, and it stimulates it, triggering depolymerization. And the reason why I think it's important, yes?
So what happens in the, at the centromere of the chromosome? How does it capture the centromere capture?
I don't think it helps to capture. It is highly strongly concentrated at the centromere, and there it triggers catastrophes, and because of that you have less stable attachment of kinetochore fibers to kinetochores, and because of that you have more possibility to correct incorrect attachments. That is, I think, the current use. So it helps because the microtubule regulation and the kinetochore is a science of its own. We are not working on this, but the idea is that you have a very sensitive system to really fine-tune microtubule dynamics there to incredible precision. And MCAK is part of that. Okay, so this is the experiment I just described. So this is more or less the same concentration of MCAK, actually a little bit higher here. And you can see that with the wild type, we don't have microtubules, and with this IPNN mutant, you have. And this is a very good paradigm which is now used by a lot of people. If you want to ask, is binding to the plus M important for my protein? That you try to find these binding motifs, which often turn out to be SxIP. We have now examples from different systems, from worms, and especially from yeast, and also from quite a few mammalian proteins. And just by making these pretty subtle mutations, you keep the protein intact, but you just inhibit this interaction. So actually what you have to do is take each individual animal, kill these motifs, and see whether something happens in a system where this protein does something. To answer another question is, so what happens to KIF2A when you target it to the tip? So this was a bit disappointing because actually in our system we were not able to see strong depolymerizing activity of KIF2A, neither when it's not on the tip or when it was at the tip. So there is some other regulation here which we still don't understand. So it didn't become a better depolymerase. It actually is not depolymerizing anything in our assays at all, while MCAK does. So that's the answer to that. Okay, and so I now end there. So it is a very complex, a flexible network, which is very dynamic, and this is what controls the behavior of individual microtubule tips. So I think that we probably should go for lunch. We can do one or two quick questions. We will reconvene here, I guess, at 2, right? Yeah. And then we will first discuss the 2 papers, and then if after that still you have some questions unanswered about this whole system, please ask them. So that we will either tell you that we don't know, which probably will be the case, but maybe there is something that also we will know. Yeah.
Right?
Yeah, yeah.
So it diffuses around and then meets the one and gets captured there.
Yeah, so this is indeed true. So Joe Howard has published a Nature paper that it diffuses. The problem with diffusion in vitro is that it is very strongly dependent on salt concentration. And they have done it with very low salt, so they have very low diffusion. Long episodes of diffusion, so the MCAK can get pretty far. So we have repeated these experiments. I didn't show you the single molecule data, but we have them. They are in the paper. You can have a look at them if you like. And what we saw, and actually what the Waterman saw and published before us, is that if you raise the salt a little bit in the direction of physiological, you see just short binding events and no diffusion. We also measured MCAK exchange at the tip in cells using the FRAP assay I showed you in the beginning of my talk. And we don't have a feeling that diffusion would be contributing much. It's all fast exchange. So yes, for almost every microtubule binding protein which doesn't bind too tight, you will find diffusion in vitro if your salt conditions are right. But whether this is relevant for your protein is another question that you should try to address. Using EBs, then it gets short, and then you still keep growing for a while, but then finally you will go into catastrophe. Another consequence of this is, and this was visible in the previous paper, but we didn't talk about it, that if you add more tubulin, the comex get longer. And this is also what you will see if you do any measurements in cells, and many of you will either do it yourself or see these images, so that when microtubules grow faster, you get longer comets. And the other way around, if you fix your cells on just staining these, sometimes you will see long comets and sometimes you will see short comets. And that's a lot of cell biologists will do this. It's an easy experiment. And what it probably can tell you is that long comets correspond to faster growth. And one way of seeing it is that when you grow faster, so you add subunits quickly, so your GTP cap is actually regulated on the one side by adding GTP tubulin, and on the other end by the decay, by some kind of intrinsic property, how quickly you hydrolyze GTP. And the first rate would depend on the rate of polymerization, because the quicker you add tubulins, the faster you grow the cap. The decay of the cap might be an intrinsic property. And then at different growth rates, you would have the same rate of decay. And then you will have a longer comet, just because you grow it faster than you degrade it. If you slow down growth, then the GTP hydrolysis catches up with growth and you get shorter comets. And if you even slow down growth further, then the hydrolysis will catch up, so you will have very short comet. And then you will also easily get catastrophe. So one way of thinking why actually you need these comets, which we have been talking around today, the whole day about, is that actually it's a kind of a protector. So actually, as also the modeling shows, you only need 4 layers or 2 layers of GTP tubulin to protect the growing end from depolymerization. But in nature, it's actually good to have a longer end and a longer comet, because if you bump into something and slow down a bit, then you will have a buffer. That's also discussed in the paper. So it's good actually to have a longer buffer, that you are a little bit prepared. If you have a problem with polymerization, you will not go into shrinkage right away. So this is all these things that, so if you think that EB proteins bind to the GTP cap, these are all the implications of this. Are there any other questions?
This seems to say that at time 0, after time 0, below a threshold level, there is a collapse.
Yes.
So is the reverse experiment also being done when you're not, the microtubule are not started growing? As soon as the EB1 level goes above that threshold level, it starts falling.
No, the other way around. So you first have to have a rescue. You don't see EB, and then once you get a little bit going, then you see EBs coming. So so EBs actually are more reporting here on the cap rather than actually, so the question whether they are doing something with it is controversial and difficult. So that's why I don't want to go into that discussion. There are data each way, in both in cells and if you, depending on who you talk to, you will find all kind of different things. And the difficulty also, of course, is that EBs also bind to the lattice. So 0 is a kind of a normalized 0. So here they scaled the images in such a way that you only see the tip and don't see the lattice. The images I showed to you earlier today, you also had lattice. I can also rescale my images in such a way that you will not see them in the lattice. Or add less EB, so you also have hardly any lattice binding. But it's always there. Also, when you label your, and I think that's the most important thing for me to let you know today, because you will be working with these proteins in cells, or seeing other people working with them see this data. So there will always be some EB binding also to the lattice. And if you don't see it, it means you didn't label hard enough. But it's always a weak labeling. Any more questions? Yes? Can you speak up a little bit? No, you cannot conclude. So this is a good discussion, and as I said, so different analogs. So this is done with gamma S. From the structure that you say?
No, you cannot say. You cannot say. What they can say biochemically, they cannot distinguish between tubulin that has GTP gamma A, a microtubule that has GTP gamma S, or GTP plus beryllium fluoride, which is a mimic of the phosphate. So they cannot distinguish, the affinity is the same. And actually, they are speculating that it's probably between GTP and hydrolyzed GTP-PI that mediate these different conformational changes. But they don't say anything, but they say both is in principle possible, based on biochemical evidence. From the structure, they cannot say that, because the resolution is not good enough, it's 8 angstrom.
Any more questions? So before we,
It may happen that it is a mixture of GTP and GTPI cap. It's a mixture, not only GTP cap or not only GTP.
Sure, absolutely. I think before we go, one very important message. This is still GTP gamma S. This is not GTP. So the Holy Grail is still not quite there, because this is a mimic of what we think is the GTP cap. But this is not a GTP cap yet. So this is where we are now at this point in our knowledge of the system. But it very well may happen that in a year or 2 years, there will be another structure where people will really try to mimic better the real GTP-bound growing tip, and things will look differently. So this is the message that I really would like to end with, that this is how we now think about the whole thing, but it still may change.
Video, I want video. Yeah.
So
Because what is the program now?
I don't think there's a lecture after this. So I think we're free for this one. I'm not sure.
Yes,